Welcome everyone, and thank you for joining us today for Digital Globe's lead webinar series, Learn, Engage, Act, and Discover. My name is Becky Schneider, and I'm the Marketing Programs Manager at Digital Globe, and I'm also going to be your host for today's webinar. But before we get started, I want to pass along a few tips to everyone to keep in mind while viewing today's webinar presentation. First, everyone is on mute. So to ask a question to today's presenter, you can use the Q&A chat box feature that's located at the right-hand side of your screen. All questions will be answered at the end of today's presentation. Attendees have the option to view today's webinar presentation in the full screen mode. If you prefer the full screen mode, you can click the full screen tab that's located at the top right-hand corner of your screen. And lastly, a link to today's webinar recording will be sent to everyone via email within the next 48 hours. Today's webinar is titled Expand Search Capabilities with 3D Geological Models. The webinar will be presented by Auracle Geospatial Science, a remote sensing and geospatial technology company that specializes in data fusion and 3D rock bear models for global clients in mineral and oil and gas exploration. Today's webinar will highlight how the 3D bare rock model differentiates rock and formation types to accurately identify and predict minerals and alteration zones. Today's webinar will be presented by David McClellan. David is the president of Auracle Geospatial Science, and he completed his postgraduate studies at SFU in Geospatial Science and earned a Master of Science degree from Manchester Metropolitan University. Since 2005, David has been an active member of the Association of Mineral Exploration of British Columbia. He is also on the Technical Advisory Committee of the British Columbia Geological Survey and is a member of the Canadian Remote Sensing Society and a fellow in the Royal Geographical Society for United Kingdom and Canada. So with that and without further ado, I'd like to welcome David, and let's begin today's webinar.
And thanks to Digital Globe for co-hosting this event. Also, thanks to everyone who's joined in. My name is David McClellan, and I'm the Senior Analyst and President at Oracle Remote Sensing. Today, Oracle exploration companies around the world are challenged by searching for larger and more remote areas without good rock exposure. Success in these cases typically depends on discovering deeper or blind mineral occurrences. The purpose of our webinar today is to explain how Oracle can help to focus your search area and evaluate potential exploration targets by integrating all of your available geoscience data, interpreting radar satellite data for structural and lithological information both at surface and beneath land cover and bedrock, and using advanced processing techniques for multiple band optical imagery to map alteration and generate targets. We'll show case examples of the mapping and modeling programs that we provide. Oracle Remote Sensing is an experienced provider of remote sensing and geospatial services for the global mineral, oil, and gas exploration and natural resource management and land use planning industries. We collect, process, and analyze spatial data collected from satellites, aircraft, drones, and ground platforms. We're fusion specialists and have developed technologies that integrate dissimilar geological, geophysical, and geochemical data sets. Our methodology penetrates the surface to go underneath ice, vegetation, trees, rocks, and till to model exposed and buried bedrock in 3D, complete with structure, contacts, and texture. This 3D bare rock model is the focus of today's webinar. Additionally, we have developed a specialized type of terrain model that we call the Continuous Surface Elevation Model, or CSEM, designed for areas with irregular lakes and streams. With it, we map the Earth's surface in its entirety, including lake bottoms for use in geophysics interpretation and modeling for mineral deposits and diamonds. By leveraging our 3D bare rock model, we have also developed customized monitoring systems that safeguard infrastructure and the environment. Oracle is part of Digital Globe's Canada Sales Network, selling basic raw satellite imagery, and standard processing services for archived or new tasked satellite images, including their new WorldView 3 spectral data. About our new relationship with Digital Globe's Global Information Products Network. We work with Digital Globe to develop customized geospatial solutions for global mineral, oil, and gas exploration using our 3D bare rock model and mineral classification maps. These relationships benefit our global clients with competitive pricing and priority satellite tasking. All optical sensors measure reflectance from ground to generate the features that we see, such as vegetation, soil, water, snow, and various minerals. Each has its own unique spectral signature which can be identified and mapped using spectral analysis tools. Visible and near-infrared and short-wave infrared, sometimes called SWIR, portions of the spectrum are powerful tools for geological applications because they cover the key absorption features for most minerals. Visible near-infrared offers two important geological applications, the detection of iron oxide minerals, which are often the only visible clue to underlying mineral deposits, and the detection of some rare earth elements. SWIR, on the other hand, allows the detection of clay minerals, micas, chlorites, and different carbonate species. Snow, ice, and man-made materials are also distinctly differentiated. By combining SWIR and visible near-infrared, we effectively can differentiate different rock types. This slide is an example in Greenland, which used WorldView 2 visible near-infrared fused with ASTER shortwave infrared to produce metallic mineral classes, color-coded using established scientific spectral libraries. In this example, the fusion was very coarse. It was derived from two different types of sensors on board two different spacecraft, collected years apart with different atmospheric conditions and different sun angles, but it still provided the needed baseline to guide mineral explorers in a very remote area that had no other geoscience available. Later on, we'll show you how an example with the new WorldView 3 shortwave infrared satellite data contains all of the necessary ingredients for vastly improved spectral analysis and mineral classification. Like the last slide, this is again a fusion of WorldView 2 VNear and ASTER SWIR data. In it, we see classifications of spectra representing various rock types. These were used to identify inliers or lithological units which were not present on the existing geological map. This is often the case as regional geological maps can be extremely coarse and not very useful to project-scale exploration. In this case, we are able to identify zones of interest based on information revealed in the data that was new to the project geologist. Similar rock classes occur on the other side of a river, upslope, which may be a continuation of the geology that was previously mapped. The other area that was discovered was just north of the brow of this hill, where an analog to the same type of geology was also located, and it was thought that it might make a good exploration target. That helped the company zone in on these two areas. Instead of spending time all the way through here, this map actually represents many, many square kilometers of ground and would have been very difficult to explore otherwise. The more spectral information we have, the more information we're able to extract and interpret at the spectral signature level. Digital Globe's WorldView 3 satellite data, which is now available in archive and new tasking, is a very significant technological breakthrough in satellite remote sensing. This diagram from Digital Globe shows that WorldView 3 has 8 multispectral shortwave infrared bands and 12 new bands called CAVIS bands that improve measurement and remove atmospheric effects. What makes WorldView 3 superspectral data special is its 8 SWIR bands, which are useful in rock and mineral discrimination. It should also be said that the 12 CAVIS bands provide for the data to be accurately corrected according to the conditions and location at the time. And these render the data as as truly representative reflectance spectra. With clean spectra comes greater reliability. Worldview 3 offers the highest spatial and spectral resolution satellite imagery available commercially. What this can mean for geological mapping and mineral exploration is quite important. It means that we are better able to compare evidence and cross-validate the hypotheses that often lead to discovery. We can use one thing to measure against another in order to detect trends and structures that host economic deposition. In these images, we can see spectra that disclose trends. On the left-hand side, we see blue mineralization with a yellow core. This is thought to be the target mineral, surrounded by bands of host mineralization. In the middle image, we see that they correlate with remotely detected lineaments, thought to be faulting. And in the third image, we see evidence of the same host mineralization terminated along a set of similar lineaments. We previously discussed the advances of Worldview 3. This is important to these images because they represent changes to the spectral spatial significance of minerals. Minerals rarely occur at surface as large homogeneous areas, but typically as small hints of patterns of mineralization. Astor's 30-meter shortwave infrared data meant that any mineral would need to be significant within a 900 square meter area in order to be detected. With Worldview 3, in this supercube data, it need only to be significant within a 6.25 meter area, which is 144 times the detection capacity. What this means to explorers is that Worldview 3 shortwave infrared data can detect mineral occurrences that are nearly 150th the size of those previously detectable. Even with Worldview 3's unprecedented capacity to map geology and alteration at scales not possible before, there is no ground penetration from the satellite, as it is only measuring reflectance of what can be seen on the surface. With optical satellite data, we detect indicators of surface minerals which tend to exhibit certain patterns, depending on the deposit type, that help to predict the presence of mineral occurrences. So while very important to geological mapping, spectral results alone do not give the full picture of what may actually be happening in the area. By integrating spectral analysis results with geological information, especially structure, lithology, and contacts below the surfaces, we reduce false positives and provide context or justification for target selection, which is the end purpose of target design. Where does the structural information come from? Let's turn our attention to radar sat imagery. Radar data is complex and does not see the Earth's surface in the same way that we see it or that optical satellites see it. This is in part because radar data is active remote sensing, which emits microwaves, and those microwaves are reflected off of objects that they do not penetrate. Because of this, many of the reflectors are not on the surface, but are at or below overburden, hills, sand, ice, vegetation, and all of the other things that we see. It also means that the radar surface model is not the same elevation model or at the same elevation as the optical surface model. The benefit to this type of data is that it does see what we don't, particularly structures, patterns, densities, and the fabric of rock that underlies the surface. This is of particular importance when we are searching for economic mineralization that is non-apparent by other means. It should also be said that radar sees the near surface in a zone that is not easily analyzed by other geophysical techniques. What is shown here are two examples of the 3D bare rock model radar. Using Oracle's proprietary methodology, complex stereo multiband radar is rendered into red-blue images that, when looked at by using red-blue anaglyphic glasses, produces a 3D image, that is, an image with depth. In these 3D images, we can detect structural lineations, domains, and continuities, even under glaciers, such as the image on the left, or lakes, such as images on the right. You can see the lines traveling through the lake. They're actually underwater. It's not a frozen lake. And on the image on the left, you can see lines that continue through and underneath the glacier. What you're seeing here are two examples of the 3D bare rock model using Oracle's proprietary methodology. Complex stereo was rendered to show us these images of the Chad Desert in North Africa. And we can see on the left the image, the optical image. It's just sand and a whole bunch of wind-blown detritus over very small amounts of outcrop. The image on the right, however, is the same area, and we can see to great depth the valleys and rock formations surrounding them that are clearly non-apparent to any optical means. Folded and faulted rocks commonly form environments for the transport, accumulation, and concentration of fluids such as petroleum and natural gas, and also zones for base and precious metal deposition. Structural mapping includes determining rock geometry based on their orientation, shape, fabric, and discontinuities. In studying structure, we give direct input over the limits, size, and shape of mineral occurrences. We understand the geometric techniques, projection of faults, geological contacts, larger trends of regional processes that control the concentration of minerals and hydrocarbons in petroleum and in mining geology. We map the geometry of structures accurately in the field and construct an accurate geological map. We measure the orientation of small structures in the field to know the shapes and relative positions of larger structures. Study the sequence of development and superposition of different kinds of structures to determine the sequence conditions of deformation. Try to apply rock mechanics data to relate structures to stresses that present in the earth at the times of deformation, and use geological data and other geology disciplines such as gravity, magnetics, and seismic to complete the work. The emergence constrained inversion geophysics has been a significant advance in exploration, but with it comes the need for accurate, concise geological constraints, which we model using this data. This structural model using fused radar and optical data provides the constraints needed to model modern geophysical data. Data types provide individual pieces of evidence that contribute to understanding the location, characteristics, and relationships in certain deposit types and their geology. The real power of these data types is tapped when two or more of them are fused together. This is the case when the whole really is greater than the individual parts. Data fusion is especially important when combining the dissimilar data that we use because the spatial data must be positionally corrected and in alignment. We support and ingest any type of data, source or format, even data collected and processed at different times, seasons, and conditions. We use a data-driven, knowledge-based form of data fusion, which requires the expert weighting of dissimilar data in their application. This results in real apples-to-apples data analysis and therefore reliable, applicable results that can lead to discovery. Why 3D visualization? We need an accurate representation of the structure, its lithological layers, alteration types, and the complexity of the bedrock beneath cover or buried at depth. A 3D geological model can provide this. This is an upgraded geological model of the area that you've just seen that was only regionally mapped and is relatively inaccessible and covered with thick tills and temperate rainforest. Even on the ground, it's difficult to see one outcrop from the other. With the 3D bare rock model, we are able to see the geology in a new way, allowing geologists to develop and search for signals in environments that are analogs to established copper and gold occurrences in the area. You can see in this area symbols that represent the structure and lithology derived from the 3D bare rock model, namely lineaments, the white lines, and strike and dip measurements that tell us about the true orientation and angularity of the faults, and also colors which represent different rock types, ages, and positions. We were simultaneously able to accurately map the watercourse networks shown in blue. And we also were able to look for analogs to the existing copper-gold occurrence from this area and over in this area, up in other areas where there were similar types of occurrence, such as this area here. Oracle has developed a specialized 3D bare rock model that combines radar and optical data. The ability to look through land cover, rock, or soils that are laying over a mineral deposit is a great advantage in geological mapping. We can expand the search for precious and base metal mineral occurrences into deeper areas. Oracle's upgraded mineral maps, structural analyses, and predictive models help our clients to narrow prospective targets and bring down the costs of making new, deeper discoveries. For operating mines, existing knowledge about the known deposit is applied to the model to identify near, but as yet unexplored targets. Given the increasing need to identify deep or buried, non-apparent mineral deposits, we help you develop a comprehensive understanding of the geometry of the structures in the third and fourth dimensions. We apply a rigorous lithostructural process to interpret geophysical or specialized geochemical data sets, then define and evaluate potential exploration target areas. Using our advanced structural interpretation skills, we connect mineralized systems to the structural setting, systematic data, and knowledge-driven mineral potential mapping, and 3D geological models. We have provided mineral exploration services for greenfields, brownfields, and resource expansion projects. Each 3D bare rock model includes a geological structural lineation and delineation. In this image, we see black lines depicting faulting with strike and dip measurements showing their angularity and orientation. The first case study I'd like to talk about is the area in central Utah where gold, silver, and copper were mined since the 1800s. The area is sparsely vegetated with rugged terrain, greater than 1,500 meters of elevation range in some areas. The lower elevations are desert, but the higher elevations get 30% of the regional rainfall during the summer. As the photo displays, the area hosts a lot of overburden, and as a result, bedrock mapping was very incomplete, and not much was known about the geological units. We fused radar, Landsat, RadarSat, Aster, and WorldView 2 satellite data to create a 3D bare rock model. It was, however, the WorldView 2 satellite data which provided the spatial accuracy and integrity that was used to align all of the other types of data. From there, we were able to fuse the data and extract information which was useful in exploration. This image displays spectral classifications representing rock types. These rock types were used to differentiate rock units in the mapping of the geology. Combined with radar information, we were able to extend rock units into the 40% of the map that was previously unmapped. A second spectral classification containing mineral classes was also overlaid, which was used to determine the minerals that were pathfinders to those associated with mineralization at the mine site. In this way, we could detect extensions to mineralization, deposit models, and other analogs for exploration. The Prospectivity Model was developed using abundances of minerals within a spatial area that included relatively high concentrations of metallic mineral spectra such as chalcopyrite, covellite, pyrite, and pyrrhotite. We further refined metallic mineral classification to map only high concentrations of copper minerals classified as chalcopyrite and covellite. Then, using the feldspar mineral classification map, areas were identified which contained relatively high concentrations of potassium feldspar. Yellow polygons were drawn around these areas and show a very complementary but also radial pattern both within and surrounding the area of copper mineralization. When combined, these elements display the patterns of mineralization and their shapes most commonly associated with porphyry-type copper-gold mineralization, which is analogous to the other established large-scale copper mines in the Utah Copper Belt. The mineral classifications, along with the 3D bare rock model, were used to type the lithologies and to build an upgraded geological map, which covered the entire area of interest. The areas which had been originally mapped as unknown bedrock or surficial geologies were remapped using the 3D bare rock model, which includes the radar signals from the SAR data and the spectral signals from the digital globe data. By combining these signals and fusing them, we were able to track the outcrop under the overburden and map those areas as well. Linear features that were extracted from the model were examined for terminations, offsets, and displacement of their spectral classes, which showed evidences of fractures and faulting. There's very little archival map faulting within this AOI, and the 3D bare rock model did reveal a significant fracture pattern correlated to the known intrusions and to previously unmapped diorite intrusions detected using spectra thought to be associated with mineralization. In this case study, you can see from the photograph in Colombia that it is typical tropical rainforest overlain with overburdened, sparse agriculture and moderate terrain. It is a relatively inaccessible area, which, due to political issues, is difficult to access. Remote sensing provided decision makers with the information they needed to focus their work, limiting their need to be on the ground for extended periods of time and their interaction with the public. Data was gathered from all possible sources to provide as much information as possible about the geology in the area. However, as is often the case, the project area was covered by the edges of two geological maps which disagreed with each other. It is not a simple task to digitize existing data, but required a full 3D bare rock model analysis. Radar images were processed into a 3D stereo set, and WorldView 2 data was fused with Aster to provide vegetation, mineral, and rock classification information. Using the sum of all these data, we were able to produce a coherent geological map and model, including information regarding target development. If you were targeting an expensive exploration program using gravity data, which of the images that you see on your screen would you think would provide you with the most accurate and complete information? As we've discussed earlier in this webinar, one of the important results of the 3D bare rock model and upgraded geological model is its application in modern geophysics. In this case, we were able to use existing airborne gravity data and perform a simple spatial constrained inversion on the data to provide you with an example of the difference that input accuracies can have on results. The image on the left is a simple projection of the archived geology map and gravity draped over our upgraded geology. That's the old gravity map. The center image shows a fracture density model and analysis showing structural orientation in the same area. By using this information, the original gravity data and the subsequent 3D bare rock model data, we were able to constrain the inversion as you see on the right. Now you can see that the area has greater color intensity. The positions are more correlated to established geologies, and you can also see that there is a relationship that defines this thrust, seeing where it's thrusting over existing geologies. The upgraded geological map shows a complete geological model without the map edge dissonance typically found in regional mapping, and contains ground verified information that is not apparent in any other area. This is a very high resolution WorldView 3 satellite image of the Mountain Pass mine in California. resolution and color are stunning and provide an extremely spatially accurate base for all other work, plus a useful product for display, recognition, and temporal evidence. It's also really important to note that satellite images like this can be used as geographic evidence of the state of an area at the time of collection and are being used in some cases by industry to fend off frivolous actions against industry. This data also contains important spectral data that can be used to generate actionable, reliable information for decision makers at all levels of industry because it is visually important and contains real information that is easy to explain and to understand. This is the same area, a larger look at the same area, and it contains the same features, the mine here in the center, and you can see the highway underneath. But this has been classified. It's been spectrally analyzed and classified into several different spectra, and the actual spectra in this, classes in this, are less important than their positioning in relationship to structure. We were using spectra in this case to examine structure for its validity, and from it we used it over top of a 3D bare rock model. Now you see in this image that we have three different details that are used to show you examples of how we use the spectra to validate structure. The one on the upper right shows the offset in minerals at the lines extracted from the radar data. The detail in the yellow surface on the lower right shows a larger area of the red mineral classes below the line and a smaller area of the same mineral classes above the line. This tells us that the movement or faulting that took place is vertical and that these have moved up or down relative to one another. And finally, the last image in the yellow circle in the center of, lower center of this image set shows just three mineral classes that were extracted from the hole. And these minerals were microcline, orthoclase, and sanidine, which represent three different temperature sets of potassium feldspar. And in this case, illustrate the evidence of termination of classes, or another type of evidence of faulting. Finally, this is the radar 3D model that was collected from the same area using a medium resolution satellite data, well actually two sets of medium resolution satellite data. And you can see from it that the type of information that we gather is somewhat different than the type that we collect from optical data. And if you look, you can see the textures and variances underneath some of the overburden that give us the evidence that we need in order to be able to map geology. The image on the left is the California digital geology draped over top of the 3D bare rock model. You can faintly see it underneath. The areas in yellow in that map represent areas of superficial geology, which means ultimately that they don't contain any bedrock information. The map on the right is the upgraded geological map. It contains far more bedrock information. You can see the smaller area, the beige area. There are two of them that are still as yet unmapped because, of course, this was using a medium resolution radar. However, you can also see that the relationships between the various different lithologies is different. It's more accurately mapped, and that it contains more faulting. The area around the mine was not mapped predominantly because of cultural effect, but the area adjacent north of the map of the mine is very well mapped in this case and shows the amount of fracturing and structure. Where we're going next, we have on our drawing board a protocol to identify depth of bedrock. We're working on that right now. We are also looking at the virtualization of the 3D bare rock model. That's being able to put it into virtual reality for viewers, and the continued development of the continuous surface elevation model to greater water depths. Thank you very much for attending this webinar. We appreciate your time. If you have any questions, please give us a call. Thank you.
So thank you, David, for your very informative presentation. At this time, we're now going to open up the Q&A portion for today's webinar. If you have a question for today's speaker, please type that question into the Q&A chat box, and we'll answer them in the order that they're received. So thank you again, David, for this wonderful, informative presentation. I did have some questions come in while you were presenting, and one of those first questions is a listener wanted to know, to what degree is the 3D bare rock model technology capable of detecting local and regional relative grain size and FASI variation in unconsolidated and poorly consolidated sediments? Oh, David, I think you need to mute your computer speakers.
Okay, we've got them muted. Thank you. Thanks for the question. The radar component is able to differentiate the granularity and texture of the substrate. In fact, it's pretty good at doing that, and that's what we use it for. As far as being able to classify the granularity and texture, we can do that as well. I would probably need some real specific examples of what you're trying to do. But if you get a chance to either send those to me or contact me, we'd be happy to take a look at the issue and see how we can solve it.
Perfect. And for that listener and for everyone else on the live webinar, I did change over to David's speaking information, and it includes his email address on that slide if you want to contact him after the webinar for additional follow-up. Moving on, another question that came in from a listener is they wanted to know what is the depth of penetration, or on the other hand, the thickness of overburden can be penetrated, and what method frequencies?
Well, thanks. Yeah, it's a commonly asked question. The issue about penetration is highly dependent on the actual substrate. So if we're trying to penetrate through house-sized cobble, obviously we can't really differentiate it from bedrock. But with small granularity and depending on the actual qualities of the material itself, in other words, there are some things like saline clays that are more difficult to penetrate, whereas dry, arid environment sands, we can penetrate to great depths. We were actually really surprised in central Colombia that we were able to penetrate so well through moist environments. And most recently, you saw the image of the lake bottom up in the Arctic. Well, the lake bottom is not a frozen lake. And realistically, we didn't know that we could penetrate through wet water using radar. Evidently, we're seeing all sorts of structure at the bottom of the lakes in that region. So it depends a lot, I think, on the contrast between the reflector, the bottom of the lake, and the substrate that's overlaying it. I know that sounds like a bit of a skirting of the issue, but the penetration is very dependent on what it's penetrating. One of the other pieces. Go ahead.
Oh, I'm sorry. Go ahead. Go ahead.
So one of the other questions Kelvin has asked is, can this technology determine the depth of a glacier or ice field? Well, actually, the Government of Canada uses it for ice field measurements and for ice depth, ice thickness measurements. And so, yes, it can measure ice thickness. I have to put in a little bit of a caveat in that. Ice also contains rock flour. And so if you're talking about glacial measurements, we have to be fairly careful that we're approximating the thickness more than we are with clear ice. I hope that helps to explain. The rock flour in the actual ice can affect the way that we can measure the thickness.
Perfect, and I hope that answered, there was a couple questions in regarding to ice, so hopefully that answered both of their questions. If not, continue chatting along with us into the chat box feature. So moving on, another listener wanted to know as far as how deep can features and structures could the 3D bare rock model technology pick up?
Yeah, well, the thing that's been really surprising is that you all saw the difference in CHAD between the optical images of the desert floor and the image of the valley bottoms inside the sand-covered desert. We estimate that those valley bottoms were about 100 meters deep or deeper, and that they were penetrated to the very depth, and that there were small water courses at the bottom. We also know that archaeologists are using these in Sudan, and we have done the same work in Sudan and able to see structures that we believed were 30, 40 meters deep. Now, obviously, we would have to drill all of these things off to prove the actual depth, and we're not going to do that. However, in the Columbia case, we were able to compare it to drill hole data and seismic data, and we know that we were getting down to significant depths, 50 meters. I hope that answers the question.
If not, then we'll just continue on and continue getting some chat comments from them. So moving on, another question that came in, and I apologize if I mispronounce some of these technical words, but a listener wanted to know if you can comment more on penetration capabilities in laterite. Laterite?
Yes.
Hopefully that makes sense.
Yes, it does. So actually, one of the issues that we run into is that we're trying to optimize the methodology that we use in that regard. Again, it's entirely dependent on moisture content because in laterites, the dielectric quality of the material, to get technical, is what we see as a reflector, and it's the resistance of that particular target mineral that tells us whether or not we're finding the bottom of our reflectance. And we're able to dial that down. So it's really a question of finding out what it is that we can get down to and through. In fact, right now we're just starting a project in Kuwait and Oman to try and expand that capacity based on other geophysical parameters. I hope that works. However, if you want a more fulsome answer to that, I'm available and quite willing to discuss it, particularly on a specific case basis.
Moving on, another question that came in, this is in regards to the satellite imagery that you're using for your studies. And interesting to know, a listener wanted to know, do you have to have like a certain or particular acquisition date of that imagery, or can you go back as far as like 10 years using the satellite imagery from then for these studies?
Well, we can where that's possible. And you know, typically what I think is being referred to is that we can look at a temporal study or a time change study, a change detection analysis. Or maybe they just want to use older data, archived data. So yeah, we can use data that is available. And so if there is data in the archive and it does fit, what's more critical to us is that we need two images, one ascending and one descending, in order to be able to do this. And if we can get an ascending and descending pair that have the right angularity according to the topography, then we can do it. And it's not uncommon for us to be able to find those from archived data. that
We've got a
help,
little more
I hope?
time left. I hope it does. They're not responding back in the chat box, so I think you're answering their questions perfectly, so thank you. We've got a little more time left, so we're going to take a couple more questions before we close out.
Sure.
Listener wanted to know, have you evaluated the ability of WorldView 3 data for alteration mineral mapping?
Yes, we have. Now, WorldView 3 data has only been around a short period of time, and we have, and some pretty noted people in the world of geoscience have looked at alteration mapping using WorldView 3. I think that one of the points that I brought up during the discussion is a critically important point, and that is this, that while WorldView 3 has 8 bands and is not hyperspectral data, but is superspectral data, one of its key points is that it has these Cavis bands. Those Cavis bands are analyzing the atmospheric column of the particular target that they're collecting. And while it's doing that, it's able to provide us with the necessary ingredients to be able to correct the data accurately. In the past, we've had to use generalized algorithms that may or may not really reflect what was going on in the atmosphere. That's so important if you're trying to come up with real reflectance data that you can rely on to be able to discriminate alteration minerals. And it's very good at detecting alteration minerals. The bands that were selected by Digital Globe were selected with that purpose in mind. So thanks for the
Wonderful.
question.
Yeah, these are wonderful questions that are coming in. Another question is, a listener wanted to know, what physical ground conditions could amplify the response?
Can amplify the response? Well,
Yes.
I think that there are a couple of different things that it really helps to have. Of course, having a lot of outcrop, if you're looking for a spectral response, is important. Having the appropriate angularity of information, so in other words, you're specifying the right angle of tasking when you shoot the data to begin with, is critically important. You know, if you're in high-ranging data, so that you've got a real high range of topography in the area, you know that a lot of the outcrop is going to be on faces, on cliff faces or on steep faces. And so it's really important to make certain that the angle that you're getting and the sun angle during collection are correct for that kind of terrain. If you're talking about radar, on the other hand, you want to make certain that the angle of incidence of the radar is relatively perpendicular to the average slope. So that's pretty complex, but it's also really important. And thanks for the question. You know, if you have any specific questions, people are welcome to email me. And there's one other thing I wanted to say. A lot of the stuff that we're showing can only really be seen wearing 3D glasses, the kind that you get at movie theaters. And if anyone would like a pair, just email me and we'll send them to you.
That's awesome.
Does that make sense?
That would be great to get a bunch of pictures of a bunch of people looking at some 3D satellite imagery.
Yeah, it's actually kind of interesting. At the trade show, we had 3D glasses, the red-blue glasses, set off to the side, and people grabbed them up like they were candy. I don't know what they were doing with them.
I don't think we want to know. But moving on, your last question for today's webinar is, a listener wanted to know what frequency, spatial resolution, atmospheric dampening, and signal strength has an impact.
Well, what frequency change? The frequency change into the SWIR band for WorldView 3 has certainly had an impact because it contains the frequencies that are known to have absorption features for minerals. WorldView 2 had a lot of information as well, and particularly some vegetative information. Now that's going to be a growing field. In my estimation, we're going to be looking at the relationship between minerals and vegetation more as we're able to analyze it more empirically than in the past. I don't know if that's the actual question, and if it's not, email me or call me and I'm happy to discuss it. As far as radar goes, we're using C-band radar. We've used X-band and L-band radar, different frequencies of radar. C-band, for what we're doing, works best. And we're also developing a multi-band radar. But the WorldView 2 SWIR band is critically important, particularly because the satellite has both SWIR and VNIR, and that means it's automatically fused. Yeah. So, yeah,
well,
WorldView.
Go ahead, I'm sorry.
Sorry about that, Becky.
That's okay. Go ahead. Finish your sentence.
Well, WorldView 3 has both. They're both on board. And so one of the real distinct advantages, in the past we've had to do this forensic reconstruction of data to try to get both the SWIR and the VNIR in place. This is the first real satellite, commercial satellite, that's been able to provide us with that continuity of data that gives us a real understanding of what it is that we're looking at on the ground. So thanks for the question.
Well, this has been wonderful, David. I want to thank you again for your wonderful and very informative presentation. And I want to thank everyone for attending today's webinar. If you'd like more information or if you have additional questions for David, I encourage you to reach out to him directly. Once again, just as a reminder, his contact information is listed on the slide, as well as I've also listed Oracle's website information on the slide as well if you'd like to go there to get more information. So that's going to conclude today's webinar. I thank everyone for attending, and we hope to see you at future webinar events.